Before getting into our last section here, I'd like to flip us back to stuff we talked about way back when in some earlier chapters like 2, 3, and 4, where we were first introducing the ideas of the mean, and in particular, the reframing of the mean as a thing called the expected value, where if we just had the one data set, whether it was like heights or dice rolls or card pulls or whatever it was, and we wanted to get a sense of what we could expect to happen on the next one, or just some value that we might not have, well, we take some measure of central tendency, in particular, usually the mean, and we'd pull that out, and we'd say, okay, we don't know anything about what's going to happen here, but at the very least, we can say it'll probably be around this central value, because that's what our things tend towards doing. And then from there, we talk about things like deviation and standard deviation and variation and a whole lot of really important information that we've spent months looking at. It got built out from that very straightforward idea of taking an average and using it as a representative. But now, we don't have to just talk about things in terms of one data value, in terms of one data set. We have two that we can work with. So, if we want to describe what's going on with our data set, in particular our y data set, the dependent variable, we can think about that in terms of both that idea we had before, as well as what goes on with our trend line. So if we think in terms of a trend line, where for now, don't focus too hard on that diagonal part there, just focus on what's going on with the y values and the horizontal line, we can get the idea of our deviation as we originally defined it, here we'll call it total deviation, as being represented by those gaps from that horizontal line up to or down to the specific values yi. So there's a lot of symbols here. It looks really scary, I know, but don't worry too much about that. The sentences actually here tell you exactly what's going on. But these are just our deviations as we've always seen them. Those are just our big gaps. Because having a data set that only hits the mean isn't a very interesting data set to study at all, and it's not a data set that happens very often in nature. So there's usually those gaps. But now, because we also have that relationship between the y value and the x values in terms of our regression line, in terms of our correlation, in terms of our scatter plot, we can break apart that deviation into two smaller pieces that we call the explained deviation and the unexplained deviation. Where that explained deviation, that's the y hat I, again, it's a really dense notation, but what that really looks at is taking that big gap and breaking it up first into the gap from the mean up to the line. That's how far off that goes, which is essentially what represents the amount of change in our y data set as affected specifically by our model. It's the amount that our model really is describing. It's what our model says happens, because without this model, we just have that constant prediction, but we don't always have those constant values. We very rarely have those constant values because they're not that interesting to discuss. And the model there tells us part of why they're not always the same. However, even though we'd like it if our model did a perfect job, in the same way that we don't always get perfectly consistent things or perfectly linear things, well, our model isn't always perfect. It doesn't always tell us everything, and that's what that remaining gap on top is. The gap from the actual value to our predicted value, yi minus y hat I, which we call unexplained deviation here, but really that unexplained deviation up to a flip in symbol is the exact same as the residual we talked about last section. Why they have different names, I don't know. It happens a lot in math and science in general that two people will discover fundamentally the same idea but not at the same time give it different names, and then a bunch of people will decide that they like the one more than the other, and now we're stuck with this nonsense. It's more confusing than it needs to be, but just understand that when we're talking about unexplained deviation, we're talking about residuals. We're talking about how far away our model is from reality. So, in a sense, you can think of deviation, the distance from a single value to what we expect, can be split up between the amount that our model tells us should happen, and the amount that our model fails to account for. Or, in another way, you can think of our model as being one that, since we want to minimize a residual, also wants to minimize unexplained deviation. And then from there, we can take that deviation and develop it a little bit more to talk about variation in much the same language. That we have our total variation being described by explained and unexplained variation, where we just take these types of terms, add them up, square them, and just like we were getting variance before, we now get variation, and we can split that up in terms of what happens overall, the total gap, in terms of the stuff the model accounts for, and the stuff the model will almost inevitably miss. Ideally, as always, this is as small as possible, so we can think of our model also as saying we want minimal unexplained variation, but it's usually going to be there. It's usually an amount to which our model just isn't perfect. It doesn't fit reality as nicely as we would like, especially when we're trying to make as many things as possible linear when very few things really are. But that's the relationship we have at play here, where, like I said, a lot of symbols, but really, we're just breaking apart things that we've talked about before into this new context where we have two data sets that we can describe, specific symbols to throw onto them, but really, residuals, deviations, not that much that's actually new. Now then, with these new symbols in mind, we can talk about an important relationship that we're going to focus on here in terms of a thing called the coefficient of determination, and implicitly its complement to the coefficient of non-determination, but we won't spend as much on that second one. Anyway, that's what we've got next.